Hello everyone, my name is Lu Dong. I'm working at PNNL with Ruby. My talk is Meteorological Environments Associated with California Wildfires and Their Roles in Wildfire Changes during 1984 to 2017. The motivation of this study is that California has experienced more wildfires in recent years, resulting in huge economic losses and threatening human health. Meteorology is the most important natural factor influencing the ignition, growth, and death of wildfires. Clarifying the meteorological environments of wildfires is fundamental to improving the understanding and prediction of wildfires and their impacts. This is the seasonal cycle of California precipitation. It has wet winter and dry summer, so frequent wildfires in California occur during summer and fall, which is the dry season. This is the area we focus on in this study, and the red dots are the each wildfires here. We use a total of 1535 wildfires in this study. This is the data we use. The wildfires is from MTBS project, and lightning data is from NLDN. Meteorological anomalies is from interim. First, we divided all the wildfires into 4 groups based on the temperature and humidity anomalies. And more than 60% of wildfires occurred under hot-dry conditions. Then we composite the wildfires in each group. We found that the hot wildfires occurred with a wave train propagation under high pressure over California, and the cold wildfires occurred with low pressure. The dry wildfire occurred with northeasterly wind and with downdraft. The wet wildfires occurred with southerly wind with updraft. And we can find that the wildfires can occur under different, even opposite environments. So the question is, what kind of meteorological environments contribute to wildfires? To answer this question, we use the self-organizing map. We conducted the self-organizing map during 1984 to 2000, and we get the most cases occurred in Node 4, showing in this pattern with uniform warm and dry anomalies, anomalous high pressure center, and northeasterly wind with downdraft. It is consistent with the composite of the hot-dry wildfires. Then we check the prediction scale of this node based on the pattern correlation coefficient with the environments at each day during 2001 to 2017 with this node. We found that about 40% of wildfires have positively correlated pattern with this node, with pattern correlation coefficient statistically significant at the 99 level of confidence. So this node represents the most favorable large-scale meteorological pattern for wildfires. Next, we show the scatter plot of the California averaged meteorological anomalies for each wildfire. We also show them in the 4 groups. We can find that the hot wildfires occurred with high pressure, cold one occurred with low pressure, and wet one occurred with updraft, and dry one occurred with downdraft. It is consistent with the composite result. And the dry wildfires occurred with strong northeasterly wind anomalies. And the hot wildfires occurred with more lightning and high energy. The wet wildfires occurred with strong convection and more precipitation. So we can infer that the hot wet wildfires occurred with more lightning, strong convection, and more precipitation. It is maybe triggered with the more lightning flashes. Next, we examine the relationship between meteorological anomalies and wildfire sizes. We divided all the wildfires into 10 bins based on their sizes. We can see in the figure 1. This is the average of the wildfire sizes in each bin, and the other figure shows the average of each variables averaged in each bin, and they all show the hot dry anomalies, high pressure, downdraft, strong northeasterly wind, and more lightning. These are the favorable environments for wildfires. Then we calculate the ridge regression of each variable with the wildfire sizes. We can see the moisture has the highest regression coefficient for the wildfire size. Then we also calculate the partial correlation coefficient between temperature and moisture with wildfire sizes. And moisture also dominate the wildfire sizes. So we can conclude that wildfire size mainly depends on moisture. Next, we focus on the wildfire change during 1984 to 2017. This picture shows the time series of the total bird area in each year by wildfires. The black line shows that the bird area by wildfires have significantly increased by about 3.6% per year, indicating a doubling of bird area in 2017 relative to 1984. And this increased trend is dominated by summer and hot dry wildfires. Then we also check the changes in wildfire frequency and size. We found that the increased bird area is dominated by the increased wildfire size rather than the wildfire frequency changes. Next, we check the linear trends in meteorological environments. We found that in summer, California has a warming and drying summer with high pressure strengthening. So these environments contribute to more and larger hot dry wildfires in summer. In addition, California also has more lightning count during this period. It also contributes to more hot wet wildfires during this period. Okay, we give the summary. More than 60% of California wildfires occur under hot dry conditions. From the self-organizing map, we found that the high pressure, strong northeasterly wind from inland and downdraft is the favorable environments for hot dry wildfires. And about 12% of hot wildfires occurred under hot wet conditions. It is associated with high equivalent potential temperature, southerly onshore flows, strongly convection, more precipitation, and more lightning flashes. The anomalies of wildfires shows that wildfire sizes is associated with moisture anomaly. And the long-term change of wildfires shows that the bird area has increased and it is dominated by hot dry wildfires in summer. And the long-term change of hot wet wildfires shows that the increasing lightning flashes may have contributed to the increased frequency for hot wet wildfires. For the future research plan for the future 3 to 5 years, the first goal of this study is to adopt and improve a storyline approach to study the role of climate change in the increased wildfire in recent years over California and constrain future projections of wildfire changes. The second goal is to use machine learning and numerical models to understand and quantify the sources of predictability for wildfires. For the future 5 to 10 years, a prediction system needs to be established for California wildfires based on the preceding atmospheric and oceanic conditions. Okay, thank you for your attention.